This meet.
Hey, looks okay? Yep. Awesome. So I guess we can start.
Okay.
Yeah.
I was happy to introduce you, but
yeah, no, happy to.
so we are happy to have Professor Ramani from computer science at UMD, who is going to talk about scientific computing, right? For machine learning, machine learning for scientific computing.
Yes.
And
Sure, and thank you for having me. So I guess this is supposed to be a slightly more informal seminar in the sense that this is, I suppose, to introduce AMSC faculty to the other people in AMSC. And I've kept the seminar a little bit informal as well. So feel free to jump in anytime and ask me any questions that you have. I'm not going to present one piece of work in depth. I'm going to present many pieces of work my students have done, relatively shallow fashion. But on the other hand, I'm on campus, so you can if anything intrigues you, you can stop and ask a question, or you can come and meet me later. Okay. So as one of my friends told me, I like to collect affiliations. So I have lots and lots of affiliations here so I still don't like the fact that it doesn't fit the full screen. Anyway, let's see if there is a hide something. No. Anyway, that's fine. So let's keep moving. So in general, we sort of scientific computing does stuff for science. And the scientific method is you have experiment and a hypothesis. You're Newton, the apple drops on your head, and you think it is gravity maybe, and then you write your equations by modeling, and then you write a bigger equation maybe as a form of a differential equation, and you do scientific computing and numerical analysis. And the basic idea there, and this is what we did till maybe the late 90s, and this is what allowed us to send rockets to the moon. Maybe early rocket sending was only at this part, and later rocket sending was here. And this was where I was trained in grad school in the scientific computing method, if you will. And you can sort of take this as an effort to find a model, y equals f of x, where x is an independent and y is sort of what you're trying to predict. And it is physics and math based. And you're trying to get there by by doing math or solving differential equations or whatever else. You have a small number of inputs, maybe boundary conditions, initial conditions, coefficients in your differential equation, and it predicts a lot of, you can use that model to predict lots of things in lots of places. Maybe 2 decades ago, it started becoming common to start doing machine learning, where you went ahead and you tried to take your data. You didn't sort of go from the observation to a model to simulation, but you just looked at your data and you said, let me try to find the functional relationship between my y and x, except I'm going to choose a functional model f, which has some unknown coefficients, perhaps theta, a collection of unknown coefficients. And I'm going to use my observed data to learn this functional form. And that was machine learning, at least in the early days. And Here, least squares were sort of the earliest way of doing this kind of stuff. And what we are trying to do is minimize some error estimate on our data and get this function model as well, which sort of fitted the data. To an extent, these two approaches lived somewhat separately, but there were sort of methods to combine them as well. And this stuff went more and more into statistics and became statistical machine learning along with other things, and we sort of also worked on this. And more recently, in the last 3 years, since the start of ChatGPT, end of 2022, we now have these deep foundational models, which also go to the library and learn everything there is to learn, and then can be queried and trained on sort of smaller data sets and made to answer all sorts of other questions. And these are totally new and almost scary. They seem to know everything. And so now the question that as a scientific computing person I had spent some time away doing a startup. And when I came back, there were all these things going on in machine learning and foundational models. So my question was, how do I keep relevant? How do I do research which is, uses all these new ideas, but doesn't throw away all the things that I used to work on? How do I sort of combine those two? And in particular, my research has sort of taken a few different directions. And in today's talk, I'm going to be mostly focusing on a set of applied problems where we take old forward models that we worked on, but make them differentiable so that we can fit them into deep networks. We'll also look at something called implicit neural representations to find structure in data. And we've also been working on generative AI with a focus on audio, because that's my sort of applied domain, if you will. I gave a talk earlier this semester, end of October, in the CS seminar. It's available online. It's also linked in the abstract where on the generative AI part of my work. So today's talk is mostly going to be on this stuff here. Okay, so that sort of sets the ground. So I'll just throw in a plug for the generative AI work we've done. So we have over a dozen papers in the last year and a half in audio, in all the top AI venues. And this Audio Flamingo 3 is a presentation we have at NeurIPS later this week. And it's open source, but it beats Google's models. It beats everybody else's models in understanding audio, speech, music, etc. Okay. So now let's come to this one element that brings scientific computing and numerical methods into deep learning, if you will. So in deep learning, one of the things is you have a guessed form of the model, which is in the form of a network of some sort. Could be a convolutional network, could be a fully connected network. And you have inputs and you have outputs. And what you do is you backprop your predicted output and the prediction you actually expected on your data set. And you use derivatives, gradient descent, to update all the parameters of the network. And You don't need to know any mathematics or differentiation to do it because you have automatic differentiation. So you just need to program your forward model into the network. And there are many frameworks, TensorFlow and PyTorch, the sort of early ones, which allow you to just program your model into this structure, and the model, the system itself computes all derivatives that you need to backprop through the system. But the models need not be the simple models which just involve ReLUs or GeLUs or whatever other functions, functions of functions. Automatic differentiation works for any function you can code up. You code up a function, and there are theorems which say that if your function had cost x, for the same cost x, you can compute derivatives of the function. If you code up a function y equals f of x, getting df over dx is as costly, and it is automatic. You don't have to write a single line of code. The compiler will generate that code for you. So that is certainly something we should think about. So let's say we created a solver for some PDE. In principle, we can cook up an error term, and we can get the gradient of anything we want in that error term with respect to the parameters of the PDE automatically without having to do any work. So perhaps we can fit this idea into something, and that was the initial step we took. There are some issues with this. What happens is the number of variables you have to differentiate and the number of things you have to maintain gets bigger and bigger. And also, the models will not learn interesting math. For example, one favorite example I give is if I wanted to minimize b minus ax in least square sense, we could, the automatic differentiator would get A transpose A times x equals A transpose B, because that's the minimizer of the least squares error. On the other hand, no self-respecting numerical analyst would solve the normal equations. They would solve maybe via rank revealing QR or something. And the automatic differentiator won't learn that. So you have to, maybe one profitable direction of research is to build templates for these libraries to learn numerical analysis, to do the backprop in some efficient way. But yeah. So of course, we are not the first to have these ideas. So automatic differentiation is a classical field. It's been around since I want to say the 90s at least. So the basic realization even came in the 70s that if you have a compiler which has implemented all sorts of functions, let's say sine of x, exponential of x, whatever else, all the derivatives are also explicitly known by simple algorithms. So you go wherever there's sine, go and put a cost. Wherever there's an exponential, do another exponential, and so forth. And you can create explicit derivatives exactly. And there is a very interesting line of work by this guy called Conal Elliott, who takes Spivak's calculus book and who sort of shows that all tensor calculus and this automatic differentiation are very fundamentally related to each other. So that's just so differentiable programming, many people have done. So Google had an effort called JAX, and there was another thing called PyTorch, which is now supported by Meta, but it's open. Both are open source, and for the most part, PyTorch seems to have won over. The Google JAX has better implementations of some scientific functions. And there is a line of work in physics, mostly solving PDEs, but I think their biggest success has been only in the Burger's equation kind of stuff, not too much more complicated stuff. Which is called physics-based deep learning or something like that. There's a book. There's a guy called Nils Thure who has published an online book, and it's pretty good. And the people in graphics also have worked on differentiable physics. They've sort of they came upon it after they came upon implicit neural representations. So they have something called Gaussian splatting for computing novel views from different, if you have a collection of photos of, let's say, a scene, to generate a novel view of that scene from that collection of photos, they have a differentiable formulation which involve Gaussians in 2D and 3D. So there is that, and there is also this neural radiance field. I'll talk a little bit later in my talk about implicit neural representations, which are a very vibrant field here. So I'll just take I'll say a quick thing. So my training actually was in mechanical engineering, and then I worked in business in a company, and a company which was, what do you call it, a beltway bandit. So the idea was any time a government agency put out a proposal, we wrote a proposal for it even if we were not trained in it. We went to the library and learned stuff, and we wrote a proposal, and we picked up on the job. And so I sort of, before I came to the university, I was trained in two things. One is solving PDEs in a certain way, but the other thing I was trained in is just to pick up something and try to understand and try to model it on my own. So when I came to the university, I was working on computer vision, and I had a research position. But when I became a member of the faculty, to show my independence, what I said is, let me pick up audio. And so I started looking at audio, but from the viewpoint of a computer vision person. And I tried to understand how animals perceive the world using audio. And that actually led to a very profitable and sort of interesting area of research. So even now we continue to work on that. And of course, there are all these proofs of existence. The barn owl can sort of pick a piece of, a mouse hiding under the straw in a barn, just using hearing, and can swoop and just pick up whatever. The bat can do amazing things, as can dolphins and so forth. And of course, we as humans ourselves can do all sorts of interesting things. You can listen to math seminars, but you can also talk. You can have side conversations. You can pay attention, whatever else as you go along. Yeah. So, and the other sort of interesting general point I'll make is, if you do anything which involves human vision, audition, etc., these problems have massive impact in the sense that it affects every one of the 8 billion people out there, right? So the math has to be correct, but also you need to be able to, you can find good applications whenever it involves humans, and speech and listening and music and so on are a rich source of problems, as is music, as is vision and so on. This is just as an aside. So now let me get to this personal story. So I commercialized some 3D spatial audio. Have any of you heard the Oculus, put on the Oculus headsets and experienced virtual reality? Math people don't like Oculus headsets. You try. Anyway, the audio in those headsets came out of my lab. So just as a thing. And so we launched a company for that. And I'd worked on all sorts of things in wave propagation, vision, audition, the fast multipole method, and so on. When I was at this company, I missed deep learning, I missed machine learning. But when I came back, it turned out in some way it was good that I missed convolutional networks, because it was easier to understand things with scientific computing background by ignoring all the ad hoc stuff which went on in CNNs, and to look at this other stuff here. Okay, just as to not have no equations in the presentation, I decided I'll at least have, to show that I have my chops as a as a PDE solver. So these are all PDEs. So I worked very closely with a Russian mathematician who unfortunately is no longer with us. He and I wrote over 100 papers on FMM, fast multipole methods applied to many different PDEs and integral equation solvers. So we covered all these, and we even have a book on fast multipole methods for the Helmholtz equation. So there is one line of work which is to take these solvers that we had and to make them differentiable, that we are working on. And here is a small sort of plug for my spring course. It's on computational audition, which essentially we revisit mathematical signal processing formulations for many problems in acoustics and audition. It'll be papers and projects course. The goal will be to revisit these problems in the light of both differentiable signal processing, differentiable machine learning, implicit representations, and also in the light of foundational models based on LLMs or new foundational models. Okay, so let's, I guess I have some repeat slides here. Let me jump ahead. So let me go to the first piece of work. So this work is with Meenakshi, who's in the audience. So one problem you have is, let's say you have a scene and you have many photographs of this scene. So the scene is a three-dimensional scene. So there's a bunch of, and you have projections of that scene into these images. The projections are essentially taking some point here, applying a matrix to its XYZ coordinates, and finding for this camera location what the projected pixel would be for that point in 3D space. And for for this camera location, you have another set of projection equations, but it is for the same 3D space. And so if you know the relative camera locations and you have all the XYZs, you don't have the XYZs of the point in the scene. The goal is not necessarily to construct the XYZs of all points in the scene. The goal is to construct a new view of that same scene, which is accurate. So you are, if I move around, I can sort of, I see you between, I can sort of somehow interpolate between this. So the idea of how to use differentiability for this is that we can take 3D Gaussians, and Gaussians have this beautiful property that if you project the Gaussian from 3D to 2D, it stays a Gaussian. So you have explicit formulas connecting the projection of the 3D Gaussian to the 2D Gaussian. So the idea of Gaussian splatting is to take a bunch of training images, perform so-called camera calibration between them, project points from these images out into the scene, put 3D Gaussians on them, and then project those Gaussians back on a training image, which is sort of, which you, and you find the parameters of the projection matrices and of the Gaussians in a way that yields the correct image. And this method has basically revolutionized gaming and model construction. So here is a video of these methods, and here is sort of you have only a few images, but you're able to essentially generate all the intermediate images as you want and go around the world. So if you are now playing Call of Duty or something else, you don't need to do explicit projection of 3D world models to left and right eye views. You can just use these Gaussian projections. And on cheap GPUs, these things can get over 700, 800 frames per second at full resolution, whereas the comparable other sorts of methods struggle in the tens of frames per second. And so this Gaussian splatting has essentially appeared in all sorts of games and all sorts of movie workflow pipelines. So this works great. But there is a problem with this. The problem is that the Gaussians only are trained on minimizing the photometric loss, which is, are we getting the correct RGB values between the scene? They do not learn necessarily the 3D underlying geometry. That error doesn't control the 3D underlying geometry. So what Meenakshi did was she added normals to the training pipeline. And so if you actually built, if you sort of did Gaussian splatting and then computed normals, you would get normals like so from the scene. But if you used her method with sort of ground truth monocular normals, the construction that you get is it gets better rendering, and it also allows for us to build meshes from the constructed models. So this is sort of a pipeline for what she does, and this was presented at ICASP earlier this year. And here are some pretty pictures for, otherwise you can't say that you're doing graphics. So let's move on. So I mentioned that, we work on spatial hearing. So we wanted to bring this idea of differentiability to spatial hearing. So in particular, I'm going to use a lot of words because, I'm jamming in lots of material here. I'm not going to be able to go into depth, but I'm happy to chat. So it turns out to do spatial hearing, what we need to do is get, if there is a sound source playing here, or the sound source playing here, even if my eyes are closed, I know where they came from because of the sound that I receive at the entrance to my ear canal comes after scattering from the room, and after scattering of my body and my ears. And this process can be characterized by an impulse response called the binaural room impulse response, where the sound, which is a function of the location of the source, the location of my left ear, my right ear, and the geometry of the room and my personal geometry, and the multipath of the sound. If I know this binaural room impulse response, and I know the source I want to render, I can go in and convolve the sound with this binaural room impulse response, and I'll get the impression that the sound is coming from there. Of course, I might, as I move around in space, these impulse responses will change. So I have to do head tracking. I have to compute this impulse responses fast, et cetera, et cetera. And that was what our previous work did. These filters are long, up to 3 seconds. Audio is at 48 kilohertz. And it's expensive to do this convolution. So you have to use various tricks. Convolution is cheaper in the Fourier domain. And this work was done by a previous student, Dimitri. The process can be done in those VR headsets, but still expensive. And if any of you have seen the movie Quiet Place, there is a game based in that world. And that game uses our technology. Many other games use our technology. I just wanted to throw that in there. So this is the first paper. What we tried to do is solve a classical problem. How many of you know what finite impulse response and infinite impulse response filters are there? I know he knows it, but others, have you encountered those terms? Okay, so finite impulse response filter is an impulse response of a physical system. So if I clap my hand, it will eventually die down, the sound. So the impulse response is finite. Infinite impulse response filters are filters which are usually come from math. They're sort of ratios of polynomials or something in the Z domain. And in principle, they could go forever. Finite impulse response filters satisfy very good physical properties. They sort of match energy conservation, whatever else you want. And they also sound natural. Infinite impulse response filters are very cheap to compute. Finite impulse response filters need to be convolved. So what we wanted to do was come up with a formulation which allowed us, given an FIR filter, replace it with an IIR filter. And we were able to get pretty good results. So one set of filters which are needed is something called head-related impulse responses or head-related transfer functions. So all of you have different shaped ears, so you have different shaped head-related impulse responses coming from different locations. So usually those are measured in a complex way. So what we tried to do is take a given finite impulse response filter and a given infinite impulse response filter and minimize some cost function between those and try to represent the infinite impulse response filter using some biquad like structure. And we were able to get pretty decent results. And so this work is with Armin Gerami. And here are some original filters, which are these finite impulse response filters, which is in blue, and the infinite impulse response estimate. That's in the time domain. This is in the frequency domain, and this is in phase domain. And it sort of matches well. And you get 3x speed up, 5x memory savings, and 5x latency improvement which is important for audio rendering on headsets and so on. And this method also works with other kinds of filters. This is a couple of sort of signal processing things which are, so this is a dual pass filter and so on. If it's not important for now, yeah. So this is sort of one problem. Another problem is trying to understand room acoustics. So as I mentioned in room acoustics, if you have a sound source, it reflects many ways. So one model which is often used is an image source model. And so here is an example. So here the source goes off, it reflects, it diffracts, all that good stuff happens. And you get multiple copies of a given sound at different places in the thing. So instead of trying to make this whole Helmholtz solver differentiable, what we tried to do here was to use an image source model. So let's say we have a source here, we have its image, we have its image here, its image here, image here, and so on. And we keep building images, and we build an approximation to the room impulse response. So now, given a room impulse response which is measured, can we find the parameters of the room which generated that impulse response, assuming that that room was a cuboid room or a box-shaped room? And so we get a room acoustic response, we measure an error, and we backprop through the solver, update those parameters, and get, so this is what the structure of that model looks like. It's the sum of delayed and attenuated impulses. And now the question is, how do we decide how to say that this impulse response is similar to this other impulse response? And in this case, we use things that humans perceive, like reverberation time. These are things architectures, acousticians use. And we use these as error metrics between two pairs of impulse responses and try to find the best one that fits. And this was published at a conference called WASPA a couple of years ago. And you can use this to solve problems like, what is the best place in a room to place an Amazon Alexa device if there are two sources, so that it's sort of appropriate for both speakers. So we had another crack at this using another architecture. In this previous paper, we used these sort of image source models. In this paper, we use something called feedback delay networks, and we use the same set of sort of optimization parameters, and we were able to find a feedback delay network which had the specified properties, kind of a thing. And this is even faster than the other one. So, and combining all of this, I have a couple of undergrads working on rebuilding the engine we had developed at the company, but using these methods. So hopefully it'll be faster, and it can be implemented in more cheaply. So now, sticking with the hearing theme, I hope I'm not boring you. Sticking with the hearing theme, what we wanted to do was to look at how humans perceive sound. So the sound comes into your ear. It gets somehow converted into a wave train, electrical impulses, which then goes into your brain, and then your brain does analysis on that, on the signal which is coming in. So after deep learning, the modeling of speech has become, or any audio has become very sort of driven by learning architectures. It doesn't sort of necessarily respect what is happening biologically. So what we wanted to do is to take the biological transduction mechanism and make it differentiable. So instead of having a very complex deep network to model the brain, we wanted to have a differentiable front end, which can do much of the lifting necessary to reduce things to feature space, and only use a small CNN to model the upper levels of the brain. And so a colleague of ours in electrical engineering, Shihab Sharma, and his students had developed a model called, based upon their experiments with various mammals, on how sound is transduced into spectrotemporal response fields in the brain. And we took Shihab's model and we converted it we wrote it out in JAX, which is this differentiable framework. And we got essentially the derivatives of that model along the way. We had to tweak various things. And so the model, the sound comes in, it goes along the sort of the basilar membrane, and the auditory nerve fibers do various things. There are nerve responses, certain things are inhibited. Something called the auditory spectrogram is created. And the auditory spectrogram goes from the cochlea into various early parts of the auditory cortex. And a wavelet transform happens on the auditory spectrogram. And a 4D representation is created. And you get some output like this. So this model had been developed by Shihab, and he had used it to explain things like the cocktail party phenomena, where you're able to pay attention to multiple conversations and so on. So what we then did is take this model and make it differentiable. And then we put a deep neural network at the end and did a couple of different downstream tasks. And we got pretty decent results with very small models. So this is a task called phoneme recognition. And our model does better than similarly sized models or even models which are 10 times larger on certain problems in this space, and also in a task called source separation. And this work was done with student Leslie Famularo. She was going to take it very far. She had very great ambitions, but unfortunately, Dolby intervened by giving her a job. And so now I'm looking for someone to complete the work after her initial results. So I have one student who started working on this thing. And so some of the things which are sort of incomplete is trying to understand values of certain parameters our model comes up with. And we found there is biological support for those values. And also our model learns different values of a parameter called cochlear compression parameter according to if the speech is clean or noisy. And it turns out that human ears also do that. It's a nonlinear system which does different things according to the kind of input which is used. And there is also an interesting thing that the kinds of the coefficients of the wavelet transform that are used for phoneme recognition are different from the ones used for speech enhancement. So this is also observed in the human brain, where you have different neurons fire for different tasks. So again, that was interesting. So this is a more classical PDE where you have an opaque object, but there are some holes inside that object, and you put a bunch of electrodes on its surface. You send a current through one, and you sort of measure the voltage at all the other ones. And this is called electrical impedance tomography. Mathematicians love this problem because it's a classical inverse problem. We wanted to see if differentiable formulation would help with solving this problem, doing the gradient descent. So this is work by Meenakshi and another student. So I had worked on this problem many years ago when I was working in the company. But Meenakshi and Pranav have worked on this problem. So essentially, when you set up the error, if you have a forward solver, for the backward solver, what you need is the adjoint problem, a solver for the adjoint problem. And you can compute the derivatives of the error from those boundary measurements with respect to this. And here is a square domain with so this is there is a circle which is sort of and you converge to it as you using the gradient descent Adams method here. So this is I wanted to say there's lots of work left to be done. I already mentioned this problem in the beginning where that you have least squares, you won't sort of do it. And I have a few other things going on, but we are sort of getting towards the end. So this is very interesting work. Meenakshi's, she was able to look at this problem called neural radiance fields, which is an example of the last thing I'm going to talk about today, which is implicit neural representations. So we spoke about neural representations. We spoke about deep learning for learning a function f of x, which takes a whole bunch of data and generalizes across them. So that is a way of using deep learning as an architecture for generalization. But another thing you can do is you can use deep networks as a functional representation. So if you have y equals f of x, you might say f is a collection of its Fourier series. So you do sine x, sine 2x, sine 3x, you add them up maybe with coefficients, and you get y. So that is a representation of the function in a Fourier basis. And as input, you gave that thing the coordinate value x, and you got output y. You can give different coordinate values x, and you'll get different answers y, but that representation will catch it. Can we do the same with a neural network? We can treat our function as a neural network. We feed it x, and it will spit out y. So, so this is, of course, maybe then your approximation theory ideas would have to be modified if you're doing L2, all these function spaces, etc. Now you have to adapt your thinking about those function spaces into the kind of functions these neural networks can represent and so on. So this work, so implicit neural representations are analog of function representations. So you have pointwise sampling, spectral bases, etc. This is a collocation representation. This is a spectral representation. So all of these map a continuous coordinate space into a signal space. So INRs replace high-dimensional grids such as videos, 3D scenes, audio data, etc., with multi-layer perceptrons. which can be trained on a single data set. And they fit with a relatively small number of parameters. And so these are very interesting for many problem sets. So they learn the network, if it is trained properly, it learns the internal representation of the scene, of the signal. And so there is another neural representation which tries to learn a latent vector. And so I have an image, say, I learn via this sort of, maybe I have a, what do you call it, a variational autoencoder. I learn this latent representation. So that is one way of learning a scene. But this is another way. This is, I give it this image coordinate, and it will spit the pixel value out here. And this is the function which represents this thing. Or if I have a 1D audio signal, I give it this value of time, it will give me this value of the signal. And if I keep changing the value of time I'm feeding it, it will play back the audio if I have the trained signal. Or if I have this kid brushing his teeth, it will learn this representation, whatever. And a particular sort of thing is this if you, instead of using ReLU, if you used something based on sign functions, activation functions, the quality of the representation comes much better. And this is a famous paper from Sitzman et al., which shows encoding sort of using the sign functions in these implicit neural representations works well. So in graphics, you have 3D scans where you have point clouds of objects. And what you want to do is you fit something called a signed distance function. The signed distance function is less than 0 or greater than 0, but it is 0 on the surface of the object. So, for example, in this room, if we build a signed distance function on all our bodies and on the floors and the walls, the value would be 0. But away from us, it would sort of represent the distance from our body, and into our bodies, it would sort of represent the distance into our body, if you would. But it is a representation of the 2D manifold in the 3D scene. So neural radiance fields came out in 2020, and they tried to model this problem using implicit neural representations. And they work quite well, but they enforce something called an iconal constraint on the equation. And it turns out that they are somewhat error prone. And Meenakshi had a very nice observation that, that viscosity solutions are used to represent iconal solutions in other domains, but nobody had tried it in this domain of fitting sign distance functions. And she has very good results showing that the method can be very well stabilized with viscosity results. She even has a theorem which we find it very hard to explain to our reviewers who are people in graphics, but she's able to show that point-wise error measurements actually lead to the convergence of the network. And there's lots of good math in there. Here is a result. So reconstructing the Mandelbrot set. So we are able to not reconstruct the Mandelbrot thing without self-intersections. Previous methods sort of intersect or form islands and so on. But our method retains the thing. Other methods get all sorts of weird junk. Our method sort of maintains a nice, so it's sort of a neural radiance field. So we are struggling to get this paper accepted into a machine learning conference because we have to explain too much to the reviewers, but hopefully it'll get in soon. And I'm going to skip this last part because we are already at 5:30, but there is also all sorts of work you can do in speeding up inference on transformers using ideas from linear algebra and so on, but I'll skip that and happy to take any questions.
Thanks so much.
And of course, here are the students who worked on all this stuff.
How do you measure the head transfer function for each individual will be different? So how do you do it for? Do they have to tune the system somehow when they buy the headset?
So it's so I have some way of measuring it very fast. I can't explain it quickly, but the classical way of measuring it is by presenting a sound from a known location and measuring it in the ear, and then using that definition. And there are a couple of students now working, including Meenakshi, working on actually trying to use machine learning and implicit neural representations to model head-related transfunction. Okay, thank you.
I guess. And I believe there is a waiting for us on the other side. Don't forget to sign. There is a sign up.